Okay. Hello, everyone. It's 3 o'clock. I'm going to get started because I've got a lot to get through. First few minutes is fluff anyway. There's still people coming in. So, welcome to the Holy Grail, a persistent hash array map tree for C++. There's a lot of words in the title. I'm actually going to spend a big chunk of the talk just explaining what each part of that means and how it fits together. So if there's any bit you're not clear on now, don't worry. So I'm Phil Nash. I'm a developer advocate at JetBrains. That means that I typically deal with the free C++-oriented products. We have C-Line, cross-platform IDE, ReSharper C++ if you use Visual Studio, it's a plugin, or app code for iOS and Mac development. We're not going to be talking about that today, but if you do want to know more about that, do catch me afterwards or tomorrow, here both days. Now, I'm also known in C++ circles for my test framework, Catch. In fact, I'm going to be talking about that tomorrow. I've got another talk at the same time on Catch 2 and what's new in that. So if you're interested, do come along to that as well. But today, we're going to be discussing this thing, hash array map tree. And I've chosen this sort of slightly controversial title, the Holy Grail, just to try and get more people in, really. And I've got this big exclamation mark at the end. Let's change that, actually, to a question mark. The reason I chose that term is because I'm going to present a data structure that my claim is it has minimum trade-offs compared to associative data structures that exist in the C++ standard library. We'll see by the end of it if you feel that I've met that claim and what that claim actually is as we go through. So the rest of the title, we're going to start drilling down on what each part of this actually means so we can build up to where we're going with it. So I'm going to start with the last word in there. I've been pronouncing it Trie. You may have been reading this Trie before. You've probably seen these before in a different context, usually a string-based tree, like a string dictionary, where you go through each character and that becomes the index into the next level down. This is very, very similar, but I will explain exactly how we apply it to hashes when we get there. The reason it's pronounced tree is because it comes from the middle of the word retrieve or retrieval. In fact, if we look at the Wikipedia entry, it says that they were first described in 1959, so it's not a new idea by any stretch. As I say, most of you probably come across them before. Term tree was coined 2 years later by Edward Fredkin, who pronounced it as tree, after the middle syllable of retrieval. However, other authors pronounce it as try, in an attempt to distinguish it verbally from tree. Because there is a bit of ambiguity, whichever pronunciation you go with, but trees with this spelling are actually like a subset of the more general tree, so it's not too bad. So you can carry on pronouncing it try if you like. I'm going to stick to tree, partly because I just like historical accuracy, but mostly because I've already become well known for catch. I don't want to become known for try as well. So there's that. All right, let's mix it up a bit. Let's talk about sets. In fact, more generally, I want to talk about associative data structures in C++, of which there are currently 8. Here's all of them. Nicely grouped together in these obvious pairings. We've got the single and the multi-value versions. I'm sure don't need me to explain what the differences are. But in terms of underlying data structure, there's really no difference. This is really more of a constraint on insertion. There may be implications, but usually it's the same underlying implementation. So I'm going to cancel these out, and we're just going to look at the slightly simpler single key versions. So we've got set, unordered set, map, unordered map. So now we have like an obvious division on the horizontal axis. We've got sets at the top, maps on the bottom. Again, in terms of the underlying data structure, there's very little difference. You can implement a map in terms of a set just by having a set of pairs where you only do the identity on the first value, the key, and that's often how they're implemented. So in terms of interesting differences in data structure, I think we can just concentrate on sets. That's my opening assertion there. Let's talk about sets. This now becomes the indivisible division of 2 different types of data structure. Before we get on to what the differences actually are, just an honorary mention to the good old sorted vector. It's not strictly a standard library associative container, but it can be used as one. And in many applications, it's still a really good choice, particularly compared to a standard set. Gives it the binary search, but with better cache locality and less fragmentation. So we don't want to rule it out, but for our purposes today, I'm not really going to consider this, although we may touch on it a little bit more later. So back to the sets. There's a few properties I want to draw your attention to. Again, it should be nothing new, but those underlying data structures, sets are not required to be implemented as red-black trees. They almost always are. I've not actually seen one that isn't. They are at least balanced binary trees. We'll come on to that a little bit later. Unordered set is obviously based on a hash table. So this leads to various other properties. So looking at the constraints on the types you put in them. With set, you have a strict weak ordering. Usually, as a result of having a less than operator, you can also provide a custom predicate. Unordered set, the types must be hashable, usually with a specialization of standard hash, and equatable, usually with an is equal operator. Again, these can both be provided with custom predicates, if you prefer. But there's sort of orthogonal constraints in the types, and sometimes that will actually dictate which structure we can use. Usually, we're more interested in the complexity guarantees, which tend to lead to performance. So set has log n on lookup. We're mostly going to be concerned with lookup today. Whereas unordered set has this really good constant time complexity on average, but when we often forget this, it can actually tend towards linear in the worst case. And we don't often actually hit that, but you can actually get into it. We will see an example of that a little bit later. But usually that constant time lookup on average is what gives us the performance, actually translates into performance. And so usually where we can, performance is a goal, we will reach for unordered set over set. And that's an important point we'll come back to a bit later. So that's a little bit of background. We're going to dig into some of the technical details of this in a moment. But I want to just move on to one of the other words in the title to clear that up. And this is persistent, or persistence. And I actually want to mention, first of all, what we're not talking about. That's why I put this picture up here. So this is me at the end of the London Marathon last year. It's definitely not the type of persistence we're talking about here. But we're also not talking about anything to do with databases, file system, networking, anything like that. That's not the type of persistence we mean. That's common confusion when people hear about persistent data structures for the first time. What we are talking about is really best explained through an example. So start with something really simple, a list. Now, we don't tend to use lists so much in C++ these days. You could say we hate lists. But they're a really useful example and still very common in functional programming languages because of this property. So let's just have a quick recap on how a singly linked list is implemented. Again, we're going to whiz through this because I'm sure you're familiar with it. But linked lists will have a number of nodes, each with a value, and also a pointer to the next or previous node, depending on how you look at it. And the first node is usually called the head, and the rest, or the first node of the rest, is called the tail. Now, what's interesting is if you want to add a new node to the head, the only thing you have to do is just write the pointer to the original head into the new node. The original nodes don't actually need to change at all. Now, we don't usually deal with the nodes raw. We usually have some sort of wrapper type, which we'd usually call the list. And they would have the pointers to the heads and maybe a size as well. So they're pretty lightweight and cheap. All the storage is in the nodes. And that means that if you perform all your mutations by actually producing a new list instead of mutating in place, you can keep the original values around. That's what we mean by persistence. The old values persist. And this is a really interesting property that usually, naively, we might think this will involve a lot of copying. And yeah, sometimes it can tend towards that. But in the best cases like this one, there's no additional copying involved with those nodes, as long as we're working at the head. And we can do removal operations as well from the head. We can stack these things up. We can get whole generations of these lists with very low cost because they're all sharing their common state. Now, of course, that breaks down a bit. If you start to do mutations further down the list, that will add up in more copying. And we don't tend to use linked lists in C++ anyway very much. It's very occasionally the right data structure, but all the pointer hopping, lack of cache locality, and that sort of thing will mean that vectors are usually a better choice. But very illustrative for this purpose. And we can take what we've just been talking about there and start to move it up by just adding a single extra pointer. So if we have 2 pointers in each node, we have a tree. Simple binary tree, like this one here. Here's our strict weak ordering, ordered from left to right. Now, if we want to add a new item to this structure, say this 4 up here, well, we just traverse down the tree to find where we need to add it in. We usually have a couple of choices. We could hang it off the 3 or off the 5, but if we hang it off the 5, then we don't need to rewrite any of the other nodes. So that's what we always do. We hang it off an existing leaf. That's nice and simple. And if this was a immutable data structure, we could stop there. But if we want persistence, we need to keep the original structure around. So we can't actually mutate our 5 node there. What we're going to have to do is take a copy of it and then write the new pointer to the new leaf into the copy. And then by doing that, we also have to write a new copy into its parent all the way up to the root. So this is a common pattern you'll see in persistent data structures, this sort of copying a path up to the root. But that's all the copying that's involved. And in a larger tree, this will actually still be sharing a lot of common state. So you end up with something like this. So we've got the entire original tree untouched over here, and then just a new path with links into the old tree. So sharing a lot of common state, usually a lot more than is shown here. So that was actually fairly easy to do. But this was a simple binary tree, and they can tend to get very unbalanced. Imagine loading up with already sorted data. You'd end up with effectively like a linked list down one side or the other. So we need some strategy for rebalancing the trees. That's why I say with standard set, it's got to be some sort of balanced binary tree. And there are different strategies for doing that. The most popular one is the red-black tree, at least in the standard library implementations. I'm not going to go too much detail on this because that's not the subject of this talk. But these are the rules if you're interested. What I do want to do is just quickly look at how that would play out with our example just now and how it relates to persistence. So here's the same example again. We've now colored all of the nodes red or black according to those rules. We can usually do that with no storage overhead, by the way. We've added a new 4 node down here, and that breaks one of the invariants, which was that no red node should have a red child. So in order to fix that, we usually consider the parent, grandparent, and uncle nodes. So we can do it all locally, with local reasoning. And in this case, we just have to recolor those nodes according to those rules. And now we've fixed that invariant, but now we've broken it again between the 3 and the 7, so we just recursively go up towards the root. That violates the black root invariant, so we recolor that to fix that. So we've just been recursively applying those. I couldn't seem to come up with a small enough example to fit on the slide that actually involved moving the nodes around. So in this case, we just recolored them, but it will often involve moving them around as well. The reason I wanted to illustrate this is because now if you look at all the nodes we've touched, as well as that path up to root, we've got a little bit of collateral damage as well. We've had to touch some of the other nodes around them. So in terms of persistence, there's a slightly higher cost with red-black trees. But that said, persistent red-black trees are a really useful data structure. In fact, consulting Wikipedia again, interesting paragraph on the page for red-black trees. It says that red-black trees are also particularly valuable in functional programming, where they're one of the most common persistent data structures, used to construct associative arrays and sets, which can retain previous versions after mutations. That's what we were talking about. Then it talks about the log n for space and time. So they are useful. I've implemented these in the past. They've been very useful for us. But think back to where we started talking about sets versus unordered sets. Usually the reason we go for the unordered sets for performance. So just because we want to make these persistent, do we want to have to give up on that performance? And that's where we're going to lead towards our hash tree. So you could actually approach this from the hash table side. You can't make a hash table in itself persistent. I mean, you can. It would generally involve copying the whole hash table. So it becomes counterproductive, really. So you might start to think, well, what about if we break this table down into chunks that we arrange in a hierarchy? And that sort of line of reasoning may take you to where we're going. I'm going to approach it from the other side, though. Start with red-black trees, which is why I've dwelled on that for a little bit too long. The problem was we've only got the 2 pointers at each node. And that puts a limit on how shallow we can make the tree. It's pretty much fixed. got that log n complexity. So if that's the problem, oh, and by the way, the implication of this, as an example, is you've got a set with about 15 million entries in it, which is not that unusual. It's going to be about 24 nodes deep. So a lot of pointer hops, a lot of cache misses. And that's where the hash tables really start to shine. But if the problem is not enough pointers, surely the solution is just to add more pointers. And in fact, that is. It's exactly what we want to do. We don't add too many, because then you end up with something like a hash table where it defeats the ability to make it persistent. So we've got to have a small enough number that we get the benefits without so much of the downside. And in fact, that's exactly what we're going to do. But it raises now a couple more questions in terms of how we implement that. And in answering those questions, that's going to then lead us to our hash tree. So what are the questions? Well, the first one is, how do we know which pointer to follow? With the binary tree, it was easy. We just do a less than comparison, go left or right. What do we do here? So let's have a look at a slightly more concrete example. So we've got branch nodes, we've got leaf nodes. Each branch node is going to have an array of pointers in. I've chosen 32 here. That's not an accident. We'll come into why in a moment. And some of those have pointers to branches, some to leaves. So what we do then is we take the hash of the key, or the value, exactly as we would do with a hash table. But this time we just peel off the first 5 bits. And that becomes the index into the array. This is why it's a tree, T-R-I-E. So in this case, that 27th bit is a pointer to another branch node. So we follow that down. We then take the next 5 bits. It gives us a new index, 6 in this case. The 6th bit takes us to a leaf. If it had been another branch, we would go down again, and we'll keep going until we either exhaust the hash or we hit a leaf. So exactly as with hash tables, we will have hash collisions. So the leaf nodes must contain an array of values, and we have to have a strategy for resolving that as well. So that could be a linear search, as you would do with a standard set. You could do other things as well. We'll come back to that point a little bit later as well. So that's where the tree comes into it, and that's how we manage to have a large number of pointers. But that leads on to the next question, which is, how do we deal with this large number of pointers? We've got, in this case, 32 at each node, and on a 64-bit architecture, that's quite a lot of space that most of the time, as you can see, it's going to be null pointers. We don't want to pay that space overhead for all those null pointers. So it sort of smells like we want some sort of sparse array to hold these, and that's exactly what we're going to do. So what we do is we have a compact array which has just enough slots for the number of pointers that we need, 3 in this case. And then we have an additional integer which acts as a bitmap into our compact array. So if you imagine a virtual sparse array of 32 slots, each unset bit just corresponds to a null pointer, and a set bits to a pointer in the compact array. Pretty straightforward. So we just use that bitmap to map by finding the bit that corresponds to the index you want, and then counting the number of set bits to the right of it. So you mask out the top bits, just count the set bits, and that gives you the index. So if you take the leftmost bit up there, there's 2 bits to the right, and that will give you an index of 2, gives you the right entry. Sounds simple enough. Then it raises another question of how do you efficiently compute the number of set bits? You could do that naively quite easily, but if you want to do it efficiently, we'll come back to that point a bit later. But that's the approach. That's where the array mapped part comes into it. So we now pretty much have the complete definition of a persistent hash array mapped tree. So we've arrived. So what we get is something like this. Again, trying to keep it simple for the slide. So I haven't shown a lot of branching, but there's a few branches there with more than 2 pointers to give you an idea. And you can see the hash codes that we've been peeling back as we go down. It's a simple path up to the root. So these are much shallower. In fact, let's have a look at some of the properties of this structure. So for a 32-bit hash, because you could have a 64-bit hash, of course, we've got a max depth of 6 or 7. Say 6 or 7 because if you're peeling back 5 bits at a time, you'll have 2 at the end, and it's probably not worth considering that part of the hash. Just leave it to hash collisions. So that will give you 6, usually. For that 15 million values example, we've got an average depth of 5, significantly better than 24 in the red-black tree case. Not as good as a hash table, but close enough. As we said, the leaves hold arrays of values because we need to deal with hash collisions. But it's more space efficient than a hash table because we're doing that sparse array. Technically, in this case, the complexity is log 32n, which sounds really awkward to imagine. In practice, for most real-world purposes, it does track much more closely the sort of, constant time on average complexity of the hash table. But it's not quite as good. And here's a bonus. We don't need to do any rebalancing like we did with the binary trees. The reason is because that distribution of our tree is going to be based on the distribution of the hash. Flip side is we do need a good hashing algorithm. If the hash is not very well distributed, then our tree won't be either. And we'll see an example of where that goes wrong in a while as well. So that's the theory. Let's actually look at some of the outcomes of all this. If you looked at the abstract on the website for this talk, there's a bit that I made this claim. I'll highlight that. Talking about hash trees, say they are close but not quite as fast as pure hash tables. That's the claim. Now, I've written a reference implementation of this. It's not complete for usability purposes, but it's complete enough to run some tests on it to see how this plays out. So I'm going to have a look at some graphs now and draw your own conclusions. So we look at the performance. So my methodology is, I used a micro-benchmarking framework called nonius.io. Since I did this a few months ago, I've actually started to add micro-benchmarking support to Catch. And I've actually converted the tests over to that, but it's not quite as rich enough to produce the graphs I needed yet. So I've kept the original graphs for now. And what Nonius does, it will run your tests long enough to be meaningful versus the clock accuracy. But then it will run a number of samples of that. Default's to 100. Some of them I've done 1,000 to make sure they are statistically relevant. And then it will do statistical analysis on that and give you the mean and the variation and so on, discarding outliers. So it's pretty good for that. Now I've used Clang with libc++. That's relevant because we're going to be comparing against standard set, standard unordered set. It's that library's implementations. So there may be quality of implementation concerns. That's all I've done so far, though. It would be interesting to see how others fare. I've started off by testing loading up one of these containers, or all of these containers, with 100,000 integers. It's a monotonically increasing series of integers. So let's have a look how that plays out. Here's the first graph. This is for insert. And the blue box here is standard set. Large green box is hash table, or HAMT for short. And then this orange bar down here, you can almost hardly see, is unordered set. But the y-axis is time, which means I'm really not doing very well on this one. It's a bit of a disappointment. I'm about 4 or 5 times slower than standard set, and about 20 times slower than unordered set. So what's going on here? Well, there's a couple of things. The most important one is that this is insert. And most of the optimization so far has gone into lookup. We're actually paying the full cost of persistence here. Every time you add a new node, you'll be copying whole paths. So it's quite a big overhead. There are some optimizations you can apply, which I've done very successfully in my red-black tree implementation before, which mostly involves a form of copy on write. If nodes are not shared, you can actually mutate them in place because no one outside has seen them yet. I haven't done that here yet. I'm fairly confident that will bring it down to at least the sort of level of standard set and hopefully closer to unordered set, but I can't quite prove that yet. So there's some asterisks around this one, but that's insert. So let's have a look at lookup then. Oh, actually, before we do that, another thing to note about these graphs is, in fact, if I go back, I don't know if you can see the black lines, which is the variance. There's actually some quite high variance in places. If you look at the scatter plot diagram instead, you can see that the orange and the blue lines are not too bad, but the green one for hash tree gets very jittery towards the end, and then right at the end, there's a big spike. There's obviously something going on my machine when I ran this. I tried to shut down as much as possible, but you can't get everything. So nonnius will exclude those outliers, but it's averaged including that second half of the graph, whereas I think it would be fairer to only consider the first half. It doesn't make a big difference in this case, but I wanted to point that out because from now on I'm just going to look at either these graphs or my aggregated views. All right, so let's look at lookup. So the same 100,000 integers, but now we're doing a find. So now the blue at the bottom is still unordered set, still the winner, but the orange on top is standard set. So green is now beating that. So we're getting closer. We're starting to get there, but it's still closer to standard set rather than unordered set. So not quite meeting that claim yet. So slightly disappointing still, but what's the problem here? Well, remember I said that the balance of the tree is dictated by the quality of the hash algorithm. So we're using a sequence of monotonically increasing integers, and we're using libc++, and its default implementation for standard hash for an integer is just the identity function, which means our hashes are also a monotonically increasing series of integers. So we've got a really unbalanced tree here. And even with that, we're beating sets. That's not too bad, but there's an opportunity for improvement. There's a few ways we can tackle this, which I've not had a chance to do yet. I did experiment with some hash remixing algorithms. They actually made things worse, so I've parked that for now. But I'm confident we can get that down as well. So let's try another example where we have better hash distribution. So what I did next was I took 100,000 integers, and then I base 64 encoded them, and used the strings resulted from that. So we've got 100,000. Oh, before we get on to that, actually, I did plot this for all the orders of magnitude between 100 and a million. We'll come back to those. So the next one is strings with the base 64 encoded versions. And here you'll see, well, the orange line at the top is set again, but the blue line in the middle is unordered set. At the bottom, the winner on this particular test is hash tree. And that was a little bit surprising. We're actually beating hash tree in this example. That's a specific case, and we're comparing against a specific implementation to say there can be quality of implementation issues. So I fully expect another implementation of unordered set to beat hash tree, but I think this is good enough to show that, at least in this case, we can be in the ballpark for my claim. A few asterisks remain, but this is really promising. I'm still a little bit worried about the integers, though. So I then took those strings, I took their hash codes, and I ran a test again with integers based on those hashes. So you've got the same distribution, but with integers. And this is interesting. I wasn't expecting such a change in the profile, but we start off with hash tree being the winner again. Set and unordered set are much closer. In fact, they're all much closer. But somewhere between 10,000 and 100,000, they all cross over until at the top, and actually, this one goes up to 10 million, by the way. Standard set becomes the winner. It's actually beating unordered set and hash tree. And I suspect the reason for this is that at this level, the hash collisions start to become significant. So I said before that linear search at the end can become significant. I think that's what's happening here. And with hash tree, it's also currently doing a linear search for its hash collisions. But what we could do is we could detect whether the type supports strict weak ordering, and then use that to do a binary search at the end. I haven't tried that yet, but I have a feeling that that will bring us down to probably beating out standard set at the top there as well. But in any case, I'm reasonably happy with that. In terms of trade-offs, I think we're doing okay. So that's the performance. As I say, I'll leave it to you to decide whether we're meeting that claim, because there are a couple of asterisks. But what I want to move on to is looking at a little bit of the code. Now, the first version I did of this talk, I actually had 90 minutes. I went into the code in quite some depth. Obviously, don't have time for that here, but there's a couple of bits I want to call out. The first one is to go back to this slide, where we talked about the array mapping. And I said at the time that the trick here is how we do the count set bits efficiently. So here's one implementation. Got this from Stack Overflow, of course. In fact, Stack Overflow led me to this site on Stanford Edu. It's a whole page of bit shifting algorithms to do just this task, counting set bits. There's a whole load of them. This one seems to be about the best on average. The more specialized cases, there are some better ones. There's no branching in here, so it's actually pretty performant. It's all bit shifting. But notice that comment in the middle. This comment's from the code, by the way. Could be substituted for an assembler instruction if available. And in fact, if you're using GCC or Clang, you can use this intrinsic built-in pop count that, with a certain compiler switch, will give you that assembly instruction. And that's what I used in these tests. So if you use the previous bit shifting version instead, everything just sort of shifts up a little bit. It doesn't really change much, except I think that the one where hash tree was winning, it pushes it slightly above unordered set. But everything basically holds, so it's actually pretty efficient. This is obviously better. And most architectures will support it, so I think it's fair. So also going back to this slide where we showed the hash table. Like we said with list, we don't usually deal with the nodes raw. We use some wrapper type, which will also include the size, so we don't have to visit everything to compute that. And in fact, what we can do in code is just capture those in a single data structure. It's going to be a pointer and a size, which on most architectures we can deal with atomically. And that has some implications. So I'll use this hash tree data structure to fit into a more general hash tree wrapper. I won't go into all this in detail, but it basically just has more sort of standard container-like wrapper for that. And all of the logic for insertion is in there as well. Where it gets interesting is I have another type called shared hash tree, and this will hold that hash tree data atomically. So we can do an atomic compare and exchange on that. And that means this can be a place that you can share between threads, and you just ask it for its current copy of the hash tree data. And because it's a copy that we can get atomically, we can then work on that off to the side and then commit it back later. And I put things in there to make that a bit easier. So looking at a test case for this, I'm not actually dealing with concurrency here, but you can see, get the shared hash tree, start a transaction, gives you back an object that you can get a hash tree from. You can then insert it in your ledger and commit it back. Now, commit won't necessarily succeed, because if someone else in the meantime has changed it, then it will say that failed, and you have to do it again in a loop. So to make that a little bit simpler, I've got this update with method, which you pass in a lambda, which gives you back the hash tree you can start modifying, and at the end it will commit it back, and we'll run this in a loop as necessary. So did I? Yes. That's the implementation of it. It's actually pretty straightforward. The calls into commit there. Commits what does the atomic exchange, but it's pretty straightforward. And otherwise, it will rebase based on the current value of the hash tree. So I've managed to get through that in time, which I was quite surprised about. Come to our summary. So hopefully I've convinced you that we can approach the performance of hash maps, even though there's a little bit of work to be done. As we mentioned, they're more space efficient than hash tables, so that can be an advantage when you're dealing with particularly large data structures. Copies are cheap and memory efficient, particularly if they're non-modified copies. They are basically just copying 2 integers. And you can choose whether the old value persists or not. You can hold multiple variations in memory at once. We didn't really delve into this, but this is a really good practical use case. I originally got into this when I was dealing with financial data, and we would have large object graphs of market data where we want to run scenarios on them. So we'd actually take multiple copies and multiple dimensions of the whole graph and make small modifications. And then you could have mostly shared common state between them. We couldn't do that all in memory before we had these sort of implementations. And there's many other use cases like that. And as we touched on at the end, can be made to work nicely with concurrency. By default, if you use the atomics, if you haven't got a lot of contention on the writes, then they can work really, really nicely. If you have, then you might need to use locks around that, but you get the choice. So they're the benefits. And that's me. There's a a list of references on my website, levelofindirection.com. If you can't remember that, I've also got extra levelofindirection.com, and that redirects there. /storage/HAMTrefs.html. So that includes my reference implementation, another one that's come up since previous talks on the subject, and some papers. So a lot there to pick out. Or you can catch me on Twitter. So thanks very much for listening.